Hi everyone. Today in this video, we're going to be diving into this concept of maintaining constant velocity. Specifically, we'll be tackling this fundamental principle of Newton's second law and how it comes into play when we attempt to maintain a constant velocity while moving. Then we will use derivations of this law to predict future translational motion of an object. So what exactly is Newton's second law? Well, it states that force is equal to mass times acceleration. Acceleration is known as change in velocity over time. Constant velocity would mean that the acceleration is equal to zero then. If we're not changing the velocity, then acceleration would not be occurring. Therefore, mass would also be equal to zero. As you can see in the bottom of this slide with derivations of our formula, we can rearrange it to where we can have final velocity is equal to the initial velocity plus the net interactions divided by mass times delta t. This is very important for being able to find future predictions and future positions of our object. We can plug our final velocity in to get final position is equal to initial position plus the velocity times delta t. This rearrangement allows us to be able to find the future translational motion of an object. As we go into Tracker, we can see that we have my basketball as an object and we have our coordinates set up. Our x-axis is set up to where it's positive going in the right direction. And then that would mean that it's going negative in the left direction. As it moves, we can see that we've been trying to track the position over time. You can see this in the bottom right of the graph. With every movement, it records the time and its position. In the top right, it seems that there is a linear trend with the graph as position is going with time. Here we are recording the initial position that we were given, and then we were recording its initial time, which of course would be 0 seconds. We are then able to record the first recorded position after that and the first recorded time. And the most important concept that we can grasp is finding the initial velocity, which is taking the two positions and subtracting them and dividing that by the change in time. Here we have negative 0.45 meters per second. It's moving 0.45 meters per second in the negative x-axis direction. Here we're going to make a computational model that shows the future motion of our object. In order to begin this though, we first have to change the mass of our basketball. Originally it was 0.1, but we changed it to 0.625 because that's the standard mass of a basketball. However, that's not really that important because we're assuming that the net interactions and forces are equal to zero, then mass doesn't really matter in this case. However, what does matter is the velocity and position of the basketball. And this is because we are gathering this data from the tracker and we're able to put it into this program. That way it knows where to begin. However, probably one of the most important aspects of this code is in the while loop where it says force net equals vector 0, 0, 0. Here we are setting the net interactions and forces equal to zero. We are assuming that it will maintain a constant velocity. So when we go and run the program, we can see that the ball and the object is indeed moving in the negative x-axis direction. And here we have a graph that shows it's a linear trend. Now, when we compare models between the computational and the real program, we can see that they're both linear, moving in the same direction. However, there are some discrepancies and there are some differences. There can also be an effect with the fact that the speed wasn't really constant to begin with. When we push the ball, it may not have been maintaining a constant velocity the whole time. What happens whenever we flip the axis, however? As you can see, when we flip it across the x-axis, the velocity of the ball and the position of the ball are moving in the plus x direction. This is different because it was moving in the negative x direction. Once again, why were we off from our prediction? Well, it's hard to maintain a constant velocity when the ball is rolling, and friction from the table could have kept it from rolling at the same pace. So in conclusion, there is no acceleration when there's no change in velocity. But usually whenever we see this, we typically see no acceleration when the object is rest. Why do we see it whenever the ball is moving? Well, that's because we're assuming that there's no net forces interacting on the ball. There's no way to tell that the number of pushes and pulls occur with Newton's second law. Newton's second law only tells us that the force net is equal to zero whenever we have a constant velocity. And we can use the velocity update formula to predict future translational motion when F net is equal to zero. Thanks for watching, and I hope you'll have a great day.